Hello, Math 120, and this is Professor Gonzalez, and I would like to go over some homework questions that you might have from homework assignment 1.2. So what this assignment covers is percentages and translating English statements into mathematical statements and solving them, and word problems. And word problems, so this section is a very challenging section for students, so I'm going to explain the best of my ability how to do these word problems. If you're able to do most of them, that's great. And if it's the longer word problems that you're having problems with, you can fast forward to that point. I've noticed a lot of people started this section and are doing okay, but there's probably a couple pieces here and there that you could use some help on. Let me start off with some of these simple percentage problems. And with these percentage problems, you typically are either dividing something or multiplying something. And the problem is that you just don't want to guess. So you can solve these by using proportions, or probably the easiest thing to do is directly translate it into an equation and go from there. Typically, I don't like the idea of translating something that by saying when you see a is, you put a equals, when you see an of, you put a multiply, when you see a what, you put an x. I don't really like that style of translating into math, but it actually is easy and simple with these specific types of problems. When they say something like, what is a percent of something? 23 is 10% of something else. 63 is what percent of something else. So in this context, it actually is kind of easy just to do it that way, and that is just translating into a phrase, into a mathematical statement. So let me go ahead and first just write this again, and let me start over here. And this says, what is 50% of 6? Now, if you know about percents, 50% of 6 is just half of 6, and the answer is going to be just 3. So that really is the fastest way to do it. But if you're confused, an easy way to do it, a more, systematic way of doing it would be to say, when I see a what, I'm going to write an x. I see a is, I'm going to write equals. 50% as a decimal is 0.50. When I see an of, I'm going to go ahead and write a multiplication sign. And then it becomes really clear. If I'm trying to find the what, if I'm trying to find this what, all I have to do is solve for x, and it already is solved for x. So all I have to do is multiply. And it just says that 0.5 or half of 6 is 3. So the answer there would be 3. The next problem would be a tougher one if you didn't have some systematic way of doing it, because it says 23 is 10% of what number? A number we don't know. And so that makes the problem much tougher. Let me go ahead and rewrite this one so I can do the same kind of thing and translate. So this one says 23 is 10% of what number? So that would be, translate 23 is equals 10%, write it as a decimal. Of means you're going to multiply that. What number? What would be x? So now we have a nice algebraic, systematic way of doing this. We've got an algebraic equation that we can now solve and isolate for x. Get x by itself by dividing both sides by 0.10. Now this gives us, 0.10 divided by 0.10 leaves us with 1x, and 23 divided by 0.10 gives us 230. So we're able to get the answer of 230. So 23 is 10% of 230. In fact, you can grab your calculator and take 10% by multiplying 0.10 times 23, and you'll get, 0.10, which is 10%, times 230, and if you do that, you'll get 23 to verify that. Okay, number 3 is going to be this phrase right here, and so I'll write it as 63 is what percent of 72. So once again, translating that, we've got 63 is equals what percent x of means you need to multiply it by 72. And so once again, because we have a mathematical equation, we can just solve for x. Isolate x by dividing by 72 on both sides. 72 divided by 72 is going to result in an x on the right, and 63 divided by 72 is going to give us 0.875. Now, when you do the problem like this, this what percent, if you just write it as x, it's actually written as a decimal. And we know that if you want to translate a decimal to percentage, you will need to move the decimal to the right 2 places, which would make this answer as a percent as 87.5. Now it is written as a percent. Percent means per 100. Okay. Okay, so that's a nice way of doing it. Of course, like number 1, if you already know how to do percents and understand them, 50% of 6, that's half, so that would really be the fastest way in that case. But you know, the problems get a little more challenging as we go, and so having a nice system, algebraic way of doing it can be very helpful. Let's move on to number 4. Translate the following English statement into a mathematical statement and solve it. So we have the sum, and we know the sum is an answer to an addition problem, and that addition problem would follow right here. So if they want the sum of a number x and 13, that would be addition. You can't just assume that when you see an and, you always put a plus. The plus is coming from the word sum. Okay, so the sum of x and 13, so x plus 13 is equals 30. So we go to solve this equation. So the first thing they want, I believe, is the equation, which is x plus 13 equals 30. Now solve the equation by subtracting 13 from both sides. And now we get, of course, 13 minus 13 zeroes out, leaving us still with an x. And 30 minus 13 is 17. So x equals 17. Okay, moving on to number 5. We want to translate this into a algebraic equation. It says, oops, this is kind of freaking out on me. Let's see, it says 3 times. Now it doesn't say 3 times a number y. It says 3 times the sum. And so that makes this problem a little trickier. The sum is an answer to an addition problem. And so it wants 3 times the answer to this addition problem, which is y plus 2. So we have to use a parentheses, the order of operations, to make that happen first. Because if we just wrote 3y plus 2, then that would be 3 times the number y and then add 2 later. But this says it wants 3 times the sum, so you have to actually add it up first, and parentheses will make that happen first. And then after that happens, then multiply it by 3. And it says this must be equal to 27. It says please write the answer and do not simplify the answer. Do not simplify when you put it into MyMathLab. So that's just going to be 3 times y plus 2 equals 27. Now we want to solve the equation, simplify it, really solve the equations, what we're doing here. So 3 times y is 3y. In this problem, we're going to use the distributive property. And we're going to say 3 times 2, which is 6. Of course, we're going to subtract 6 on both sides of the equation, leaving us with 3y equals 21. Finally, we divide by 3, and we get y equals 21 divided by 3 is 7. So y equals 7. Moving on, the difference. Now the difference is the answer to a subtraction problem. And some of these formal operators like that, sum, difference, quotient is the answer to a division problem. Product is the answer to a multiplication problem. So if it says the difference between W and 21, it wants to know the difference, which is subtraction. So W minus 21. Okay. And it says that it equals 4 times W. It says equals, and then it says 4 times W. So now this is the equation we're looking at. W minus 21 equals 4W. Now we need to simplify this by solving it. Solve for W. So I'm just going to subtract W on both sides of the equation because I'm trying to get W on the same side. If you subtracted 4W, that's fine. You'd have maybe an extra step involved. But as long as you're doing it to both sides, you're fine. We end up getting negative 21 equals 4W minus 1W is 3W. We divide both sides by 3 to isolate and get 1W, and that equals a negative 7. Okay, moving on to number 7. So number 7, now we're starting to get into bigger word problems, and maybe some tougher ideas in some ways. So let's talk about this. In order to do this problem, first of all, you need to know what consecutive integers are. That's the first thing you need to know. So what is a consecutive integer? So consecutive integers are integers that are basically in order. So if I say 3, then consecutive integers would be the next, or 3 consecutive integers, if I start with 3, would be then 4 and 5. Integers are also negative whole numbers, or whole numbers in their opposites, probably a better way to say it. So if I said negative 1, then the next integer would be 0, and then the next integer would be 1. If I said I'm going to start at 10, 3 consecutive integers would be 10, 11, 12. So something that you'll start to see, if you want to try to generalize this, then you would say, well, if I'm going to make x my first consecutive integer, notice the pattern. If I want to go from my first consecutive integer to my next, oops, that's a funny thing that just happened to that, I just add 1 to it. So if I want to go from my first consecutive integer of x to my next, it would just be add 1. And if I want to go from my first consecutive integer to the third consecutive integer, I would have to add 2 to that first one, right? I know you're just adding 1 when you're going from first to second, then add 1, then add 1, and add 1. But we always want to refer back to the first x. Add 1 gets us the second consecutive, and add 2 gets us the third consecutive. So that distinguishes the first, the second, and third are going to be different numbers. So in a problem like this, we would do something like that. We'd make a let statement, and if they don't have that let statement on in my math lab now, that's so you're not going to be held to it. But usually we like to define our variables. Let x equal what? The first consecutive integer. And then we're going to let x plus 1 be the second. This is the second consecutive integer. And then we're going to let x plus 2 be the third consecutive integer. So algebraically, we're saying that we've got the first consecutive integer is an x. We've got our next or second consecutive integer is going to be plus 1, x plus 1. And our third one is, compared to our first, is going to be x plus 2. Well, look at this problem. They're saying that they want the sum of 3 consecutive integers. Well, sum means you're going to have to add them up. And they're going to say that when you sum them up, it adds to 132. So, here's our equation. So this is a big part of solving a word problem is turning that question into an algebraic equation. And we defined our variables there. Now that we have this algebraic equation, right, we can solve it. We can solve the algebraic equation by combining like terms. I've got one x, I've got another x, I've got another x, I've got a total of 3 x's. In terms of my constants, let's go to green here. Looks like I've got a 1 here and I've got a 2 there, so that's plus 3. And then of course we have, whoops, that's erasing. Of course we have our equal signs. And it says that equals 132. So that is our equation simplified. We simplified the left by combining like terms. And now all we need to do is solve the equation. Subtract 3 from both sides. Of course it zeroes out here, that's a 3. So on the right we've got 129. And of course we still have our 3x. And continuing to solve, we divide by 3 to isolate the x on both sides. This gives us x equals 129 divided by 3 is 43. So we like to define our variables because we want to know what is x, by the way. Let me go back up here and it said, we said that x is the first consecutive integer. Oh, okay. And remember, go back to the question. The question says find these 3 consecutive integers. Well, that means that 3 consecutive integers are going to be 43, the next one is 44, and 45. So you just did something, you just did 2 things, 2 requirements happened. These are consecutive integers, and guess what happens when you sum them up? When you actually add them up, and you can go ahead and try this, you will get 132. So those 2 pieces of information or requirements had to be satisfied in this problem. They're consecutive in order, integers, and then when you add them up, you get 132. So that is the answer to that problem. Let me write it right here. That would be 43, 44, 45. Okay, let's take a look at number 8. So number 8 says, suppose that you just received an email alert from a website indicating that a 4 gigabyte flash drive have just been discounted by 60%. If the sale price of the flash drive is now $9.40, what was the original price? So very often with these problems, like I would say 99% of the time, the question at the end is going to be your variable, because that's what you're looking for. Now, it doesn't always work on every problem, but it's super high percentage of the time. This is going to be your variable, meaning let x equal the original price. Let x equal the original price. Okay. I'm making it worse. Every time I touch that, it gets worse. Let me try again. Let x equal the original price. Okay, so there are a couple ways of doing this. And what I like to do, so let x equal the original price. So basically what we want is we want to get, so okay, here's how I like to do the problem, and it streamlines it, but I'll kind of show you a way that a lot of books show also. Maybe makes more sense to you. Let's see. If you're taking, so x, let's go back to my color. We're saying that x is the original price, so we're saying x is the original price. Well, if you're taking 60% off, what are you left with? Well, you're going to be left with 40%. So really what we want is 40% of the original price. We want 40% of the original price. And they're saying if you take 40% of the original price, that is $9.40. So 40% of x is $9.40. You can start to see the equation forming here based on those early problems that we're doing. You could translate this into a mathematical statement, which would just be change the percent to a decimal, 0.40 of would be multiplied by x is $9.40. And now solve for x by dividing by 0.40. Reduce 940 divided by 0.40 gives us 23.50, and we know that this x is defined as the original price. So we would say $23.50 was the original price. Okay. Let's see here. Okay, so another way to do this problem, if you want another way, if that 40% didn't make sense, the other way that quite often math books would do says let x equal the original price. So you start with the original price, right? And then what do you have to do? Well, you have to take away. So if it says that it's a discount by 60%, you have to find 60% of what? 60% of that original price. So you've got your original price, and then you have to take away this discount, which is take 60% of the original price. And they're saying in the problem that when you do that, your result is going to be $9.40. So now the question is, what does this become? Well, this is a 1, and if you want to write it as a decimal, it'd be 1.00, like a dollar. And this would be 0.6 or 0.60, like 60 cents. And so if you subtract those two, you end up getting 0.4 or 0.40. X equals $9.40. And that is exactly what I had right back there. Okay, so this problem's done. All right, let's move on. So, of course, if you solve this, you'll get the same answers I got on the left. Let's take a look at the next problem, which is number 9. And this says that Juanita has $26,000 to invest in two accounts that pay simple interest on an annual basis. One account pays 4% in simple interest, and the other account pays 5% simple interest. How much would she have to invest in each account to earn a total interest of $1,100 after 1 year? So this problem requires you to understand simple interest. So let's just take a quick look at that. Simple interest, an example of simple interest would be if I told you that the bank would pay you 10% per year, 10% per year simple interest. Well, then if you had, let's say, $200 in the bank, they would give you 10% of $200. So you just multiply 0.10 or 0.1 times 200. And so simple interest after 1 year, if they said 10% simple interest, that would be how much? $20. Okay, multiply 0.1 times 200, you get 20. So that's simple interest. It's not compounding interest, it's simple. So now what makes this harder is you've got these two different accounts. So my visual, I guess, that I do with this is we're starting with $26,000, right? There's your pot of money. And some of it's going to go over here at this 4% rate account. And some is going to go over here at this 5% account. Okay. Now the question is usually going to be the variable. And the question at the end was, how much would you have to invest into each account? Now, I remember when I was a high school algebra student, the teacher said if you don't know something, you just put a variable there. And that's kind of true, but we don't know how much is in this account, and we don't know how much is in this account. And so in high school, I would have just put an X there and a Y there, and then in the end, I would have too many variables. Now, if we were in the section called System of Equations, where you have two variables and two equations, that would work great. But we're not in that section. We're in the section that we're working with linear one variable equations. And so if I let X equal the dollars in the 4% account, I got to show the relationship of this other account. So let me think how I can do this. Let me put a little graphic over here on the side. Let's see. Yeah. I'll do this in another color just to show it's not really part of this problem. $4 account, and then this is the 5% account. Okay. Darn it! I need more space there, and I just scrunched it over too much. So if you're starting with $26,000, right? This is the connection between the dollars in both accounts that we have to show in our equation. If you're starting with $26,000, well, what if I told you the 4% account had $10,000 in it? How would you know what the 5% account has in it? I still think I'm out of space with this thing. I better really come over a bit. How much would be in the 5% account? Well, you'd probably just tell me it must be $16,000. And if I asked you how you did it, you'd say, well, if you start with the original starting amount was $26,000, and I deposit $10,000 into the 4% account, well, then what's left goes in the 5% account. So 26,000 minus 10,000 is 16,000. Okay, so that procedure is the connection is whatever you put into the 4% account, how do you get what goes in the 5% account? Well, it's going to be the original total minus whatever you put in the 4%. Okay, let's do one more of those. If I put in 20,000, now these are not the answers, it's just trying to get us to see the relationship between the dollars in account, the 4% account, and the dollars in the 5% account. There's a relationship, and we have to show that. Right? Another way to look at it is 10,000 times 16,000 gives me my total amount of money. So what if $20,000 was in the 4% account? Well, then the other 5% account, we know how much is in there because it's going to be the 26,000 starting amount minus that 20,000 that we happen to put in the first account. So that means the 5% account would have to have 6,000 in it. Okay, so that is important to see that connection, because when we go to a variable, and I'll go ahead and use red, I guess, for this. We go to a variable, if I said there's X dollars in the 4% account, well then how much in a variable, or what's the relationship, oh boy, I'm having problems here. What's the relationship between how much is in the 4% and the 5%? Well, if X is in the 4%, then what goes in the 5%? Well, it's got to be the total, which was 26,000, minus what was put into the 4%, minus what was put in the 4%. So that means that is what we have. Okay, so we've got X dollars in the 4%, and if there's X dollars in the 4%, then there has to be 26,000 minus X dollars in the 5%. And that's because the sum of these two accounts must add up to 26,000. Okay, so then the next piece is we want to calculate how much money is in that account, and they're telling us in this problem the total has to be $1,100. So if you want to figure out the value in the account, remember at the beginning over here, how did I find the value? Well, I took the percent as a decimal times the amount, and that gave me the value. So if I want to know how much interest, or how much simple interest was gained over a year, well, it's going to be my interest rate, which is 4%, which is 0.04, times the dollars in that account. I guess I'll just go with the color here. The dollars in that account, it happens to be X. And then what I'm going to do, this might be confusing having that. Oh, that's a dollar sign. That's what that was, dollar sign. Then I'm going to have to add that up, because the amount of money that I make, simple interest, is going to be right here. And then I'm going to make some more simple interest out of this account. Well, what's that going to be? Well, once again, it's the percent as written as a decimal times the amount of money in that account. Okay, so the amount of money in the first account is this amount. The amount of money in the second account is this. And it's telling us it better equal $1,100. So this is our full equation. Let me simplify this. 0.04 times X plus. Now in this one, we're going to have to distribute 0.05 of 26,000. So if we say 0.05 times 26,000, what do we get? We get what, 13? Yeah, we get 13,000. Okay, so we distribute the first term and we get 1,300 rather. And then we distribute to that last term. Don't forget the negative. So this is going to give us a negative 0.05x. Now that's going to equal, as the problem said, 1,100. Okay, now what we want to do is we want to combine like terms. So we can combine like terms by first identifying the like terms, and there they are right there. 0.04x minus 0.05x is going to combine to make a negative 0.01x. Of course, we still have this plus 1,300, and that equals 1,100. We're going to solve for x by subtracting 1,300 on both sides. Of course, that zeroes out, leaving us with this on the left, negative 0.01x. And when you subtract 1,100 minus 1,300, we actually end up with a negative. And that might be a little bit disturbing, because you know that there can't be a negative amount of money in the account. But when you isolate for x, you've got to divide by that number in front of x, which is a negative. And when you divide both sides by this negative value, you're going to see that a negative divided by a negative will give us a positive value. And so negative 200 divided by negative 0.01, that gives us positive 20,000. These are dollars. Okay, so let's go back up here. If this account, and we just found out this account has $20,000 in it, then how much would be in this account of 5%? Well, it's going to be the original 26,000 minus 20,000, so that leaves us with 6,000 in this account. And so there's the answer. Let's go and write that out down here. It means we're going to have $20,000 invested at 4% and $6,000 invested at 5%. She would have invested, up here I'll just answer it in the problem, $20,000 at 4% and $6,000 at 5%. This is simple interest. All right, let's move on to the next problem. Jane has been saving quarters and dimes. She opened up the piggy bank and determined that it contained 41 coins worth $8.15. Determine how many dimes and how many quarters were in the piggy bank. So once again, determine how many. Now this is really a little bit tricky here. How many? So with these kind of problems, the thing that you have to really, really make sure you're careful of is that there's a couple ways of calculating this stuff, right? How many is talking about the quantity of coins, but then you could also talk about the value of the coins, right? So there's two things going on. So let me take a little note on this, just a side note, just a maybe, and I'll do this in green. We have a total coins. What are the total coins? 41. This is going to be the quantity, the number of, and so we might want to say something like number of dimes, right? That's not the value of them. It's not the dollar value of them, but it's the quantity of how many there are. And we might want to say number of quarters. Number of dimes and number of quarters. Well, just like the last problem, if we know how many dimes there are, then we will definitely also know how many quarters there are, because they both have to add to 41. It's a lot like the last problem. So like for instance, if I told you I have 10 dimes and I have a total of 41 coins, you can easily figure out how many quarters there are, because you would say, well, there's a total of 41, darn it, there's a total of 41 coins, right? I'm just going to write that 41 all the way down. There's a total of 41 coins, and if you used 10 of those coins over here as dimes, right? There's a total of 41 dimes and quarters, so if 10 of them are dimes, well then the quarters are going to have to be 41 minus 10, which is then going to tell us, what's that? That would be 31 quarters. So that relationship is something you have to show in this problem. Let's do another one to make sure we understand that relationship. What if there were 20 dimes? Now, if there's a total of 41 dimes and quarters, and 20 of them are dimes, that means that the number of quarters are going to have to be 41 minus 20, which equals 21. Okay. let me get rid of this. Now, dot, 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 dot. Let's move it on down. What if we wanted to know, what if we didn't know how many dimes there are? That's this case here. This question is we don't know how many dimes. So we let x equal the number of dimes. So the question is, do we know how many quarters there are? And many people would say, no, we don't know. But there is a relationship that still needs to be shown, just like we did when we knew that there was 10 dimes, so there's 31 quarters. There's 20 dimes, so there's 21 quarters. Well, if there's x dimes, then there must be 41. I'll do that in another color. There must be 41 total minus x quarters. And so if you can get that is a key idea. That relationship has to be in your math. So we're going to let x equal the number of dimes and let x, oops, I'm sorry, I just messed that up. Let 41, oops, let 41 minus x equal the number of quarters. Okay, so let's see, the next piece we want is we now want to know the value of this, because, so let's use another color. Let's use purple. So if I want to know the value, so we already covered the 41 coins, the total, the number of coins, but now that's the value. So if I want to figure out value, well, if I want the value of, let's say, dimes, let's get an overall idea here. The value of dimes plus the value of quarters, the value of quarters must equal, in this problem it says $8.15. So now the trick is we've got to figure out what is the value. Well, the way you find the value of dimes, like for instance, let me go back over here. If I had 5 dimes, someone said, what's the value of 5 dimes? Well, you'd have to say 5 times the value of a dime, which is 10 cents. So the value of 5 dimes is 50. So with the decimal, that's going to put a decimal there. Let's kind of make sure when you use a dollar sign, you're going to use a decimal, and this is symbolizes 50 cents. When you don't use, or when you use the cent symbol, you don't use a decimal. So those two things are equal, but they're just using cents, which is out of 100, and then dollars, which is not. So you have to have that decimal there. Okay. So let's just continue with this value idea, quarters. If you wanted to know the value of 4 quarters, and most people know that because it makes a dollar, but you have to take 4 and then multiply it by 0.25, and that gives you $1 or 100 cents. So same thing over here. If we want to know the value of the dimes here, you have to take the number of dimes times its value. So the value of a dime is 10 cents. And how many dimes do we have? Well, we defined it back here as X dimes. Plus the value of quarters. Well, the value of quarters is going to be 25 cents. And how many quarters do we have? Well, we defined our quarters as 41 minus X. And then finishing the problem out, it says that all must equal a value of $8.15. Now we have a nice algebraic equation, which was really hard to get to, but now we rely on our algebra to continue. So let's simplify that. It's just 0.1 or 0.10, I'll just call it 0.1x, plus we must distribute, so 0.25 times 41, and 0.25, what is that? 0.25 times 41. I think it's 1025. I better double check real quick. Don't want to make a mistake now. So 41 times 0.25 is 1025. So we distribute this and we get $10.25. Then we distribute the next piece and we get, don't forget the negative sign, we get a negative 0.025 times x, and that equals 815. So now let's simplify the left-hand side of the equation by combining like terms. These x values are like terms, and when we combine those, we've got 0.1 minus 0.25. So in a sense, it's like saying 10 cents if it helps having a little zero there in your mind. It's like saying 10 cents minus 25 cents, and that's going to leave us with a negative 15 cents, or in this case, 15x. We still have our plus 1025, and we have it all equal to 815. Let's continue to use our algebra to solve by subtracting 1025 on both sides. And then we take 815 minus 1025, and that leaves us with negative 210. So now we go ahead and solve for x by dividing by this value right here in front of the x, its coefficient. So divide both sides by negative 0.15. Oops, negative point. Divide by negative 0.15, of course that reduces down to 1x to get our answer. And when we divide negative 2.10 divided by negative 0.15, we get a nice 14. Now we go back to our defining of variables. It says let x equal the number of dimes. So that's going to mean that we're going to have 14 dimes. And then, let's see, 14 dimes. And how do we figure out how many quarters we have? If we have how many quarters we have, it's going to be 41 total quarters minus the 14 dimes. So if we want to know quarters, it was 41 total coins minus 14 dimes, right? 41 minus 14 gives us 27. So that would be 27 quarters. So we go back to the original problem, and what was the answer? Go ahead and put it in. 14 dimes, 27 quarters. Okay, two more problems. The next two problems are called linear motion. And with linear motion, you're going to need to know, I'm going to put a little note, I'm going to use some color coordination. You're going to need to know that rate times time equals distance. And in these problems, I'm going to use some different colors. So for rate, I'm going to use a red R in this case. And for time, I'll go ahead and use green. And distance, I guess I'll just leave as, let's make it blue. So this shows us that rate times time equals distance. And so you've got all these three pieces that you need to kind of keep coordinated, and knowing that they have this relationship of rate times time equals distance. So let me kind of clean up that D, distance. Okay, so a picture is going to be really worth a lot here. It says two cars traveling towards each other are 325 miles apart. Car A travels 15 miles per hour faster than car B. So I'll try to draw a picture that kind of illustrates this. This is car A. It's going faster than car B, so it must have gone further This is car A. They start here. It's going faster than car B. Here's car B. It's not going quite as fast, so it didn't quite go as far. And so this is car B. And so I said I was going to use distance in blue, and it says that look back at the original problem. It says the cars are they start 325 miles apart. Car A is traveling 15 miles per hour faster than car B. The cars pass each other in 5 hours. So when they say pass each other, they mean when they pass each other, they are exactly, right. Essentially what it means is, let me use blue for distance. When they tell us that the distance is 325 miles, it means, the big picture is if I could figure out the distance here and add it to the distance here, that must equal 325. There's sort of our big goal. Now we're missing a lot of stuff here. Now we have the total distance. Do we have rates? Do we have time? We do have time because they're telling us that the cars pass after 5 hours. That means that car A was traveling for 5 hours and car B was also traveling for 5 hours. So they're both traveling for 5 hours. Okay, I'm seeing a distance, at least a total distance. What about rate? Rate is going to be the tricky one. And they did give us a nice clue. It says that car A is traveling 15 miles per hour faster than car B. So I'm just going to say this is the fast car. This one's faster, just to help us see that a little bit. So you can let x equal the speed of A, the fast car, or let x equal the B, the speed of the slow car. Either one will work, but it will be easier to call x the speed of the slow car, x miles per hour. The reason why that's easier is because if you want to show the relationship between the slow and the fast car, well, they told us the fast car was how much faster? 15 miles per hour faster. So it makes it really easy if you make the slow car x, the fast car is x plus 15. I always have someone, at least one person in the class ask, well, what if I make x the fast car? Well, then the slow car would be x minus 15, and that works just fine too. But now you've got a negative or a subtraction, which is usually not as preferred, but it just works just fine too. So that's a reason why we define our variables, right? Because we want to make sure that we know is x car B speed or car A speed. So I'm going to go ahead and define the variable real quick. I'm going to say oops, gotta get a pen that works. Let's go ahead and let x equal car B's speed. And then we want to let x plus 15 equal car A's speed. And of course, this stuff is, in my drawing as red because red is rates and rates are speeds. All right, now, I would really be in good shape if I knew what the distance of this piece was right here. And oh, by the way, I do know the relationship here, right? I do know the distance because distance just equals rate times time. So if I knew, remember, distance equals a red rate times a green time. And we do know that, so let's do it. The speed that car A traveled is we define that variable as x plus 15 to define the speed of the car of car A as x plus 15. We also know that how long did it travel for? Well, it traveled for a time of 5 hours. So rate times time or times rate actually is a distance. So now this little expression is actually the distance that car A traveled. And if I could, figure out the other distance, I could just add the two up. So let's see, how do I figure out the distance of car B? No problem. Do I know its rate? Yes, I do. Its rate is x. How long did it travel for? Just as long as the other car, 5 hours. So 5 times x is the actual distance that car B traveled. Well, car A's distance plus car B's distance equals the total distance, and that was 325 miles. We've got ourselves a nice equation, an algebraic equation that we can solve. We want to distribute 5, so we get 5x. We want to distribute 5 times 15, which gives us 75. Of course, 5 times x is just 5x equals 325. I want to combine like terms. 5x and 5x will give us 10x plus 75 equals 325. I want to solve for x, so we're going to do that by subtracting 75 off of both sides. When we do that, we're left with 10x on the left, and on the right, 325 minus 75 is 250. We're almost there. Divide both sides of the equation by 10. Reduce, and we isolate x equals 250 divided by 10 is 25. So this is where our defined variables is really helpful. What was x? Car B's speed. I'll write it like this. Okay, car B's speed is 25 miles per hour. And we also realized back here, car A's speed, x plus 15, you could also see it here, car A's speed is 15 miles per hour faster. So we just add 15 to this, we will get car A's speed. 15 miles per hour faster would be 40 miles per hour. So, go back here. Car A's speed was 40 miles per hour, and car B's speed was 25 miles per hour. All right, let's finish up strong with number 12, another linear motion problem. So we're definitely going to be using rate times time equals distance. On this time, I almost always like to draw a picture, but using a chart with these kind of problems are often very useful as well. Drawing a picture, using a chart, organizing data. Both of those organize data, organize our thoughts. Two boats leave a port at the same time. One travels north, the other travels south. The northbound boat travels at 8 miles per hour faster than the southbound boat. We got some similar things going on here. We've got a port. The northbound boat is faster, so it's going to go further. The southbound boat is not as fast, so it's not going to go as far, so I'll show that with my picture. The difference on this problem is, I believe, let's see. So let's start to get some of these let's see, some of the data. The northbound boat travels at an 8 miles per hour faster. So remember rate, we're using red, so let's continue with that. Faster than the southbound boat. If the southbound boat is traveling 21 miles, well, they tell us, okay, that's different. So the southbound boat is 21 miles per hour. Last time we had used a variable here. And then they said the northbound was faster by 8, so 21 plus 8 is 29. 29 miles per hour, right? The southbound was 21, and they say that the northbound boat is 8 miles per hour faster than the southbound. Well, that's okay, so it's 21 plus 8 is 29. So we got that data. How long before they're 100 miles apart? They're telling us that the distance we want to check out is when they're 100 miles apart. So it's 100 miles. Okay, once again, what's going to happen here is we're going to need to get this piece, that distance of the northbound boat plus the distance of the southbound boat, add them up, and it must equal 100. Okay, this time I'm going to use a chart to show it. You don't have to. And once again, we'd like to organize our data. Rate times time equals distance. And so this chart is nice in the way that it will help us organize all of this stuff. Okay, we have what? The northbound boat. Got the southbound boat. Using my colors. Northbound boat's speed is, look at my drawing, 29 miles per hour. Southbound speed, 21 miles per hour. Time is the question, so that is actually going to be our variable. And the question is, how long is it going to take? We don't know, but we do know the times are the same because they leave the port at the same time, and then we want to know when they're 100 miles apart. So the time is going to be the same. The distance we don't know, but wait a minute, yeah we do, because we know what? We know that rate times time equals distance. So this distance that the northbound boat is just going to be rate times time. It's just going to be 29x. That represents a distance. And rate times time is a southbound boat distance. So 21x represents the distance. Once you know x, it is actually a distance. So we can see from our picture the distance that the southbound boat went right here, 21x, plus the distance that the northbound boat went, 29x, equals the total distance, 100. So 21x plus 29x is, what's that going to be? 50x. Okay, and now all we have to do is solve for x by dividing by 50. And look how nice that is. X equals 2. So what was x in our problem? Oh, I never defined it. Let x equal the time the boats have traveled. The time the boats traveled. Okay, so we just figured out the problem. How long did they travel for? 2 hours. And there it is. Whew, that was a long video, but I like to really take my time and explain, especially when you come to word problems, because they are challenging for most students. This is Professor Gonzalez signing off, and you have a great day.